we are at the moment in a new part of the course, this part here, concerning the response, aeroelastic response as static response and dynamic response.
Professore,
schermo.
Yes. I'm convinced that I share the screen. It's very strange. Okay, excuse me. So response and together static and dynamic response. Yesterday we talked about the stream solutions in aeroelasticity, and so namely trimmed static solution, and we organized yesterday election in two parts. The first part, assuming, as part one, assuming to impose an angle of attack and then see what happens to the elastic body with an initial angle of attack as imposed. Just like the experience in a wind tunnel. Okay, imagine to have a cantilevered beam or cantilever wing, and then turn on your wind tunnel and then see what happens. This was useful to see that this kind of problem is, if linearized, it's just algebraic problem. It is a linear algebraic problem. And as a second step, we have considered the aircraft as a free body, and then we consider to have correctly a weight of the aircraft as assigned, and then see what happens by imposing that the vertical velocity of the aircraft be zero, in the sense that we want the aircraft be trimmed vertically. So these two problems which was faced yesterday, first solving the first one. Solving the first one problem, we introduced the influence of the angle of attack in the problem, and we see what is the consequence on considering a variation in the angle of attack on the boundary condition. And this influence was an influence on the variation of the normal on the body, and this normal so is rotated with an angle which is equal to the angle of the angle of attack, of course. And so after this analysis, we realized that the final problem is here summarized in the solution of a linear algebraic problem with a matrix like that and a right-hand side vector like that. In the right-hand side vector, we have the angle of attack, of course, imposed. And so we solve this problem linearly, and we have a solution in terms of Lagrangian variable, so describing the deformation of the body. But this is not the true problem. The true problem is a trim problem. You have a free aircraft subjected to the weight, force, and the aerodynamic force, and you want to include that this body is a flexible body. So we have the same equation, but we, in this case, want to introduce also one more equation and one more unknown. The noun is the angle of attack. The equation is the rigid body vertical equation of motion. Consider only also that the mode of vibration are different in this case, because here we have the mode of vibration of the free structure and not of the constrained structure. Okay, so we have written our Lagrange equation of motion like here, and we have emphasized the fact that the first equation is the equation of the rigid body motion, and so we have this equation plus another vector as a load vector given by the weight force. So the first component for the first equation of the Lagrangian input is the weight. Okay. So here we have demonstrated that we have a set of generalized variables, and the first one is given by the weight, but all the other ones are zero. And so we have n+1 equation and n+1 unknown, because we have n Lagrangian variable plus the angle of attack to be determined, to be suitably determined in the trimming condition. Of course, this first kind of trim condition is a very simplified trim condition with only one trim variable, the vertical displacement, which is imposed to be zero. Okay, and therefore we may solve this problem. And if you analyze the first equation, we have clearly the balancing of the following three contribution: the contribution to the lift of the elastic deformation or flexible deformation, the contribution of the rigid body part as given at zero angle of attack. So if you have zero angle of attack, you have in general a contribution to the lift. Typically this should be very, very close to be zero. And then the contribution of the angle of attack as a rigid body, of course. All these three contributions are able to generate the final value of the aerodynamic force, and this final value of the aerodynamic force in the vertical direction, which is the lift, is asked to balance the weight. Okay, so essentially we have this contribution here as given by the lift. Excuse me, is given by the deformation variable. Okay, but this is not the reality, because in the reality we have an angle. In order to balance the pitch, we have to use the tail horizontal surface, and we want to use the modification of this horizontal surface in order to balance the global aerodynamic pitch moment. And so we introduce one more trim variable, as you know, by flight dynamics, delta. But you have to introduce, of course, one further equation, and the second equation to be introduced is the rigid body motion equation with respect to the pitch axis. So the moment with respect a y direction axis. And we have defined this quantity as to be as phi variable, so a pitch angle like phi here. And this angle is a further rigid body variable together with the vertical displacement Q0. So these two variables in trim condition are set to be zero, this zero and this zero, if you want to balance your aircraft longitudinally, okay? So essentially we are considering the final equation for trimming an aircraft longitudinally. And as a final result of this, we have as a final unknown, the angle of attack and the delta angle to be considered in our analysis. So how this delta angle is able to be involved in this formulation? Okay, let's review again this final equation that we considered yesterday. We have, of course, in this case, n variable and stress space variable given by the modal coordinate. The first plus two more modal coordinate corresponding to the rigid mode, which is the vertical translation and the pitch with respect to the angle. And correspondingly, we have two equations. The first one is exactly the same as before, the equilibrium to vertical motion, and the second one is this here is the equilibrium to the vertical, and this is the first one is the equilibrium to the pitch. So I have numbered the pitch equation like -1 and the vertical as 0. The other 1, 2, 3 are the rigid body, are the elastic, mode numbering of our unknown, number 1, number 2, and so on, elastic mode. But these first two variables, Q sub 1 minus 1 and Q0, are set to be 0 in trim condition. So here we are imposing the trimming condition, and therefore these first two columns of this stiffness and aerodynamic stiffness, we could name the generalized aerodynamic force matrix evaluated at zero frequency like a aerodynamic stiffness, if you want. Okay, so this aerodynamic stiffness matrix, which is the GAF matrix at k equal to 0 at zero frequency, this is a stiffness matrix practically, and we don't need to the first two columns of this matrix because we are imposing a trim condition, but as forcing term, as a right-hand side term here, we should have something like that, which is a term considering, remember that here we have, this is the normal wash contribution due to rigid body motion, which is angle of attack at control surface, angle of attack and delta. Okay, this here. In fact, we have this novel term, this new term here, which is the contribution to the normal wash given by this delta. angle associated to the control surface, for example, of the aircraft. This is the aircraft, and this is the tail of the aircraft. So we have the wing here, and this is the tail. How can we calculate this? Essentially, this is due to the product between I dot what we know N1 evaluated at XCJ. Remember here, yesterday, we defined this contribution as the contribution due to the rotation of the surface. In this case, yesterday we consider a global rotation of the wing of an angle of attack, but you can specialize this concept on the control surface only, not all over the body, but only on the control surface. Okay, and so considering this variation, we have a contribution like of this type, C number 2, but now as applied to the control surface only. And so we have a vector which is almost 0, but not 0 where? Only in the control point. Only in the panel correspond to the control surface. Okay? And so we have again the same kind of system, algebraic system, of n plus 1 equation by n plus 1 unknown, algebraic linear system. Of course, you can't see this system in a standard form like that, not in the standard form like ax equal to b, because you have two unknown here multiplying this vector and the other unknown here as Lagrangian variable, but overall you have all linear relationship, and then you can recast this equation in order to have a system in this form here, but the system is absolutely linear. Okay, and so one can face this kind of solution. So essentially, in the aeroelastic trim, you are able to determine the deformation, deformation of the aircraft in straight flight, for example. So the Q variable, and determine also the value of angle of attack and characteristic surface, control surface angle for trim your aircraft to ensure zero vertical motion, Q0, zero pitching. Okay, so this is the elastic trim, and you have some commercial code like Nastran, for example, commercial code like Nastran are able to perform this kind of analysis. So implementing a finite element model for the aircraft and the panel model for the lifting surface, These commercial code are able to implement this static analysis, static response analysis. And static response analysis means static structure a static structure means only stiffness, and static aerodynamic together, which means GAF matrix at zero frequency. Okay, and for just as an information, for the commercial code Nastra, this kind of analysis is performed by the solver 144. Okay, which is the aeroelastic solver in MC Nastra. But the reality may be more complicated for aeroelastic response analysis. So let me do a comment about this point of very general type. And what I mean here, in general, we have to consider nonlinear effect. Let me do a comment on nonlinearity. In fact, we have nonlinearity. Linearity in structure and in aerodynamics. In structure, we have linearity given by large displacement, and so we have the so-called kinematic nonlinearity. But also nonlinearity given by the constitutive relationships. Nonlinearities and also so-called physical nonlinearity is given by the constitutive relationship. And this is the structure case. In aerodynamic, we may have nonlinearity occurring with, for example, transonics or transonic flow, viscous effect, turbulence, separated flow, and so on. In all this case, imagine to be able to represent with a model this kind of physics, you probably will be able to have a final problem described in this way as an evolutive problem of this type. With this is where f is a nonlinear vectorial function of the state space vector x. Of course, this step here from physics to mathematics is not completely easy, but it is possible in such a way, okay? At the end, you have an evolution of your state, the vector x, which is dominated, governed by a nonlinear set of equations. Okay? And so also the elastic system could be regulated by a question like that. If you were a very good mathematician or scientific expert on, you probably would be able to obtain this nonlinear model. And this nonlinear model should be dependent on the flow condition of flow characteristics. So you should have a parametric dependency of this vector f by u, which is the f flow u infinite. Okay, so this is a very, in general, I may expect something like that in the case of nonlinear model. Note that we have studied a linear model up to here. Everything is linear here. Here is linear algebraic for the steady state condition. But in general, we have a nonlinear problem. When you have a nonlinear problem, it's always possible to find the steady solution. The steady solution x is a point in the state space such that f, by definition, f of xe be 0. Okay, so when you want to find this problem is the problem of determining your equilibrium solution, just like the trimmed solution in elasticity. Xe is the trimmed solution in elasticity, or equilibrium solution in a straight flight. So the first step is searching of the equilibrium solution, okay? And the second step is an expansion, is a potential expansion of your solution in the neighborhood of the equilibrium solution. One could consider an expansion of f function in the I'm talking about a Taylor expansion in the neighborhood of exe. Okay, and therefore we have fx is equal to fx in the equilibrium solution plus the gradient of fx evaluated in the equilibrium solution by x minus the equilibrium solution plus higher order term. Now this quantity, this gradient, what is this gradient? This gradient is a matrix. If we are talking about in the n-dimensional space, discretized space, we have an n-dimensional state space vector. And so we have here this gradient defined like the derivative of f I element with respect to the xj state space variable evaluated at x equal to xe, and this is just like a matrix like A ij matrix, ij component. If you consider this difference between the actual state space vector value minus the value at equilibrium solution, we have a variable which is this difference, and we can give a name to this variable, like for example xi variable. Okay, and this xi variable is a function of time, of course. So what's happened to this original nonlinear model? If you consider this definition, the definition is define this new variable as equal to the old one minus the equilibrium, you have that the x variable is equal to state space variable is equal to the position of the equilibrium solution plus the perturbation c around the equilibrium solution. This is a function of time. This is a function of time, but this is not function of time because it is the equilibrium solution, not depending on time. And so if you take the first derivative of this c point, since the derivative of c equilibrium is 0 by definition of equilibrium, you have that c dot is equal to this quantity. I am expanding f, so I have f equilibrium, but f in the equilibrium is 0, remember, so we have 0 plus a c plus higher order term. And what is this? This is the so-called linearized dynamics. This is my linearized dynamic in the neighborhood of an equilibrium solution. The linearized dynamic of my system. And this is the full dynamic as described with all the nonlinear term included. The full nonlinear dynamics. Okay, I want to invite all of you to consider this whiteboard because I think that this is important for your life in general. In this whiteboard, I am clarifying what one has in mind when talking about nonlinear dynamics in general and a linearized version of the dynamic. Okay, so my conclusion to this work is the following. We can, as a consequence, describe the aeroelasticity of generally nonlinear system at 3 level of accuracy. Accuracy. And this is the point. First level, the higher level. The higher level is consider the fully nonlinear model. So means please x dot equal to f u infinite as a function of x at a given initial condition. Study this problem as this could say consider the Navier-Stokes plus Nastran solver sol 400. Nastran sol 400 is the solver for nonlinear structure. This kind of solver at the end will take into account a model, an evolutive model, which could be reduced in this form. And this is the fully nonlinear model. Second step, second level of accuracy. You could consider the title of this model is statically nonlinear and dynamically linear or linearized model. What does it mean? You should be able to understand this after the previous whiteboard. Indeed, static nonlinear means find equilibrium solution like using f of x e equal to 0. Okay, so find your equilibrium solution by using a nonlinear static structure model and a nonlinear static aerodynamic model. So find, for example, your steady solution with a shock wave on your aircraft with viscosity, lambda shock wave, with vorticity like here. Okay, so study this equilibrium solution. So use nonlinear but static aerodynamic, and use nonlinear but static structure model. Okay, and find this. Then solve the dynamic around xe by using c dot equal to ac, where x is equal to xe plus c, and a is given by taking the gradient. So through a perturbation procedure, the gradient of f with respect to ij fi xj for x equal to x equilibrium. So this is a statically nonlinear, a dynamic linear or linearized model. This is an intermediate model with the fully linear model. In the fully linear model, the stability of the equilibrium solution is identically equal to the stability of any equilibrium solution, remember? And so the third level, I stop here. We have here a model which is fully linearized. Fully linear or linearized. And this is the model we are considering. Here in this course, I want to open your mind on this kind of modeling, because what we have done in the previous theory concerning the static aeroelastic response, we have found here an equilibrium solution for the aircraft in the flow, but including only linear model. But you could evaluate this solution, this equilibrium solution, by considering nonlinear aerodynamic and nonlinear structure, and, for example, to find iteratively your solution, just iterating between your aerodynamic code and your structural code. Okay, you should do this, and around this solution you could find a linearized version of your model, and so reduce the study of the stability in the neighborhood of this solution by evaluating your gradient matrix A, and then study the A of your final gradient matrix A as solution of your problem. And this is an statically nonlinear and dynamically linear model for your aircraft plus flow condition. Okay, stop here, have a break together.
Scusi professore, posso farle una domanda riguardo la parte